So my aim on this lecture to consider Gaussian measures on Hilbert spaces, prove one important result about integrability for Gaussian measures, and discuss properties of the Cameron-Martin space. To describe Gaussian measures on Hilbert spaces, I need some notions of operators on a Hilbert space. Okay. So for now, let X be a separable Hilbert space. I recall what is a compact linear operator. It is a linear operator that sends any bounded set in X into a relatively compact set in X. So any compact operator is bounded. Well, and I recall how we define the norm of a bounded linear operator. For compact self-adjoint operators, the Hilbert-Schmidt theorem holds. It states that there exists an orthonormal basis in X that consists of eigenvectors of operator A. In other words, we can write A as the sum over all eigenvectors En, the sum of some numbers lambda n times inner product x En times En. And if the space is infinitely dimensional, then lambda n converges to 0 at infinity. From this, we can get the so-called polar decomposition of a compact operator. So if operator A is compact, then there exists a compact self-adjoint non-negative operator T in X, and a linear isometry that is defined on the range of T into X, such that A is equal to the product UT. This is an analog of writing, let's say, any complex number as a product of exponent, which is the analog of isometry, times a positive number R. So to get the polar decomposition, consider the product A adjoint times A. So this is a compact operator because the product of a bounded and compact operator is compact. Also, this product is self-adjoint. And this product is non-negative because if we consider in a product of A star AX and X, this is equal to the norm of AX squared. So by Hilbert-Schmidt theorem, we can write the product A adjoint A in some orthonormal basis that consists of its eigenvectors. And define T. In fact, it is the square root of A star A. So now numbers lambda n are non-negative because operator A star A is non-negative. So we can take square roots and define operator T in such a way. It is also self-adjoint, non-negative, and compact because lambda n converges to 0. Okay, and now let's compute the norm of Tx squared. It is equal to the sum of lambda n times inner products xen squared, which we can see is the same as the inner product of a star ax and x, which is the norm of ax squared. So hence, norms of tx and ax are equal, and this means that we can define u of tx as ax. And this is a well-defined operator, because if tx is 0, then ax is 0, and u is isometry. Okay, so we get a polar decomposition of any compact operator. So next class of operators are Hilbert-Schmidt operators. They can be defined as follows. These are linear operators for which the following supremum is finite. And this supremum, then it is called the Hilbert-Schmidt norm of A. The supremum is taken over all orthonormal systems, and this is the sum of norms AFN squared and the square root. In fact, since any orthonormal system can be extended to the orthonormal basis, it is enough to take supremum only with respect to orthonormal basis. And in fact, it is enough for a linear operator to be a Hilbert-Schmidt operator. It is enough that there exists some orthonormal basis for which the sum of norms en squared converges. And in this case, this sum of squares, it is actually the same for any orthonormal basis, and then it coincides with the Hilbert-Schmidt norm. This can be checked by the following trick. So assume that for some basis, the sum of squares converges, and consider another orthonormal basis. Write every norm AFN squared, so expand it into the basis E, so that we get a double sum. And then we can put A on EM and take the sum in N. In this way, we will get the sum of A adjoint EM squared. But if we start not from Fn, but from En, we will also get the same sum. So for any orthonormal basis, the sum of squares of A is the same. Any Hilbert-Schmidt operator is compact. So let's check this. I recall that a compact operator can be also defined as such that sends any weakly convergent sequence into the strongly convergent sequence. So it is enough to check that for any sequence xk that weakly converges to 0, weakly convergence means the inner product of xk with any other vector y converges to 0. Okay, so for any such sequence xk, axk must converge to 0 in norm. So consider such a sequence xk. So note that the adjoint is also a Hilbert-Schmidt operator, which we actually showed in the beginning of this slide, and compute the norm of AXK. Norm of AXK squared expanded into the basis En, and write each summand as the inner product of xk and A adjoint En. So here each summand converges to 0 when k converges to infinity. And also we can bound this by norm of xk times norm of A adjoint En squared. And also recall that weakly convergent sequence is bounded. So by dominated convergence, we get that AXK converges to 0. Okay. And one more class of operators. Not yet. So if A is Hilbert-Schmidt, then it has a polar decomposition. And note that the norm of A En squared, if En is if En is formed from eigenvectors of T, since U is the isometry, it is the same as norm TEn squared. And this is lambda n squared. So we get the following description of Hilbert-Schmidt operators. A linear operator is Hilbert-Schmidt if it is compact, and in its representation as the product of U and T, the sum of squares of lambda converges. The sum of squares of lambda is finite. All right. And next type of operators are called nuclear operators. So again, consider a compact linear operator A and write its polar decomposition. If the sum of lambda n is finite, then the operator is nuclear. It's called nuclear. And these operators are exactly what we need to describe Gaussian measures on Hilbert spaces. So this definition is not intrinsic. So let's prove another characterization of nuclear operators. A compact linear operator is nuclear if and only if the following supremum is finite. Supremum is taken of sums of absolute values A, Fn, Gn. And here we take all possible orthonormal systems Fn and Gn. If this is the case, operator is nuclear. And in fact, this so-called nuclear norm coincides with the sum of lambda n, where lambda n are eigenvalues of T. So first, assume that A is nuclear, write it decomposition. Then if we consider two orthonormal systems Fk and Gk, write this sum of inner products as sum of inner products of Tfk and U star Gk. Okay, and actually this is equal to lambda n fken, because en is the eigenvector of T. Now estimate these products as 1/2 of sum of squares. And now if we take if we take the sum in K, this will be just this will be less than the norm of En squared. Okay, so sum will be less or equal to 1. And here put U on En. Again, since G is an orthonormal system, the sum will be less or equal than norm of UN squared, which is also less or equal to 1. So we get an estimate that sum of lambda n bounds the supremum. Hence, the supremum is finite. And conversely, assume that A is compact and the supremum in the definition of nuclear norm is finite. Then write the polar decomposition of A and consider two orthonormal systems. One will be the basis En, and the second will be the system UEN, which is also orthonormal since U is isometry. In fact, U is defined on the range of T, so we take only n for which lambda n is bigger than 0, such En they belong to the range of T. And then sum of lambda n, this is the sum of inner products. Then we can apply isometry U to both multiples and get the sum of AEN UEN. Such sum is less or equal than the nuclear norm because both systems are orthonormal. So now, using this notion of nuclear operators, we describe Gaussian measures on a separable Hilbert space. I recall that last time we get the Fourier transform of Gaussian measures in the form of exponent IAY minus 1/2 ry times y. Here A is the element of the space, the mean value, and R is a bounded linear operator in X. Also, R is self-adjoint and non-negative. In fact, this operator R is nuclear, which is a stronger property than just boundedness. Okay, so let's verify that R is nuclear. At first, we check that it is compact. Again, so assume that we have a sequence of vectors that weakly converge to 0 in X. Then let's find the product RXK. So this is by definition of covariance operator. This is equal to the integral of xky squared minus xka squared. And we note that it converges to 0. Of course, this part converges to 0 because xk converges to 0 weakly. And here, for every y, the integrand converges to 0. And also, these integrands are uniformly integral. one can estimate, let's say, the fourth moment. I recall that the norm of the functional the norm of the functional which multiplies by x in every LP is estimated by a constant times the norm of x. Now, weakly convergent sequence is bounded, so we can uniformly estimate higher moments of xky, which means that we have a uniformly integrable sequence that pointwise converges to 0. So integrals will also converge to 0. Okay, and in fact, the norm of Rxk can be estimated by the product Rxk xk. This is because R is non-negative, so we have a Cauchy inequality. So this is less or equal than Rxk xk square root times R of Rxk Rxk. And the second factor can be bounded by the norm of A, the root of the norm of R times the norm of Rxk. Okay, so then we get an estimate, and we proved that this converges to 0. Then Rxk will also converge to 0, so R is compact. Since it is self-adjoint and non-negative, we can write it as a sum over eigenvectors. And now it remains to check that the sum of lambda is finite. So the sum of lambda is the same as the sum of Ren, which is the following integral. Now, if we write the sum under the integral, we get the integral of norm x minus a squared. And now we need to know that this integral is finite. We will show this. In fact, we will show the so-called Fernic theorem, which gives a much stronger result about the integrability of the norm. But we will do it a bit later. Now, the converse is also true. So if we have a vector in X and the self-adjoint non-negative nuclear operator, then there exists a Gaussian measure with the mean A and a covariance operator R. So a Gaussian measure on a Hilbert space is characterized by the mean value and a covariance operator, which is now nuclear, which must be nuclear. To get such a measure, again, expand R into its eigenvectors and consider the mapping that sends every sequence of real numbers into the following element of space X. Of course, the series may not converge. In fact, they unless we are in some trivial cases, this series will not converge in Hilbert space X. However, recall the standard Gaussian measure on the space of sequences, which is the product of a sequence of one-dimensional Gaussian measures. And for almost all sequences with respect to this measure, the f will be defined, because if we compute the sum of squares of coefficients, we get sum of lambda n xn squared. And if we integrate it with respect to the measure gamma, the integral is equal to 1 now. So we get sum of lambda n, which is finite. And now if we write it as follows, we deduce that for almost all x, the sum of lambda x squared is finite. So hence we can define the image gamma, which is the image of gamma infinity under f, and this will be a measure on x. And recall the Fourier transform of gamma infinity, which is e minus 1/2 sum of lambda n squared. So it is defined for all L, which have only finite number of non-zero components. So now if we compute the Fourier transform of gamma, let's say for a finite linear combination of En, we will get such integral, and then we find that this integral is indeed exponent iay minus 1/2 sum of lambda n yn squared. But this sum, this is exactly ryy. So we obtained the needed Gaussian measure. Okay, now let's complete the proof of nuclearity by proving that actually exponent of the norm of x squared with some multiple alpha is integrable. And here alpha is bigger than 0. To find this alpha for which the integral will be finite, let's do the following. So fix tau, this will be the radius of a ball whose measure is bigger than 1/2. And it turns out that one can take alpha as well, 1 over 24 tau squared, logarithm of c over 1 minus c. C is the measure of a ball. So c bigger than 1/2, hence alpha is bigger than 0. Of course, this implies that one can integrate the norm in any power with respect to Gaussian measure. One can integrate exponent in any with any positive coefficient of norm x. And all these integrals are finite. This the main property of a Gaussian measure that implies such strong integrability is that it is rotationally invariant. When we discussed the Ornstein-Uhlenbeck semigroup, we used such property that if we have a centered Gaussian measure, we proved it in finite dimensional case, but in general, the proof is completely the same, just computing the Fourier transform. And if we, one can imagine this as follows. We have two independent random elements in X, and we consider their difference divided by root of 2, and their sum also divided by root of 2. Then these two elements, they will be independent copies of X and Y. In other words, if we consider the following transformation, that takes two vectors and map them into the difference over root of 2 and the sum over root of 2, then product of two identical centered Gaussian measures will not change under this transformation. Okay, now consider the product of two probabilities of two measures. So the measure of a ball of radius tau and the measure of the complement of the ball of radius t. And applying this transformation that doesn't change the measure, this product is equal to the following to the measure of the following set. So this will be the set of all vectors uv such that the norm of u minus v over root of 2 less or equal to tau, and the norm of u plus v over root of 2 is bigger than t. But if these two conditions hold, then the norm of u, which is 1/2 norm of u plus v plus u minus v, okay, it will be bigger than t minus tau over root of 2, because this norm is bigger than t root of 2, and this norm is less than tau root of 2. And in the same way, norm of v will be also bigger than t minus tau over root of 2. So we get an estimate that the measure of the ball of radius tau times the measure of the complement of the ball of radius t is less than the measure of the complement of the ball t minus tau divided by root of 2 squared. And this allows to get good estimates on these measures of balls. So consider the following sequence. So t0 is tau, tn plus 1. So at each step, we add tau, we multiply by root of 2 and add tau. Tn plus 1 is equal to tau plus Tn root of 2. And also consider such a probability Pn. This is the measure of the complement of a ball of radius Tn divided by C. And I recall that C is exactly this. Then Pn is less than Pn minus 1 squared. Cpn let's write C squared Pn. This will be exactly this product for T replaced by Tn. And we estimated it as the measure of the complement of the ball. I need to subtract tau and divide by root of 2, but then I will get Tn minus 1. Tn minus 1 squared, which is equal to C squared Pn minus 1 squared. So now if we iterate this estimate, we will get that Pn is less than P0 to the power 2 to the power n. Okay? This means that the measure of the complement of the ball of radius Tn is less than such quantity. And note that 1 minus C over C is less than 1. So these measures, they converge to 0 at a very high rate. Now this allows to estimate the integral. So the integral from the integral of exponent over the complement of the ball of radius tau, we can split into the sum of integrals exponent alpha norm x squared d gamma x. So integrate over x, whose norm is bigger than t, less than Tn plus 1. Then we can estimate integrand as exponent alpha t squared n plus 1. And we will get the measure of this set, which we estimate by the measure of the complement of the ball of radius Tn. So we obtain the sum. This is the estimate of the measure of the complement of the ball. And this is the explicit expression for T n plus 1 squared. Okay. Then write it under one exponent, and recall that alpha is 1 over 24 tau squared. And here we had logarithm of c over 1 minus c, which can be written as 1 minus c over c, and with minus. Under exponent, we have 2 to the power n log 1 minus c over c, 1 minus say root of 2 plus 1 squared, I believe, over 6. And now the coefficient, the value in brackets is positive, logarithm is negative. So we obtain the convergent expression. Okay. And in the next part of the lecture, recall the some properties of the Cameron-Martin space, or reproducing a kernel Hilbert space of a Gaussian measure. The Cameron-Martin norm is defined as supremum of L of H, where L is a continuous linear functional, and its variance is less or equal to 1. L R L, this is the integral L of x minus a squared d gamma x. And the Cameron-Martin space consists of vectors for which the norm is finite. And we proved last time that it actually coincides with the space of all such integrals. X star is the closure of linear functionals in L2. I mean, the closure of centered linear functionals in L2. And as we showed, the operator R acts as an integration of fx times x d gamma x. Okay, so this was last time. Actually, if the vector h can be represented as Rg, so the integral with a functional g, so such function is unique, and we can define the inner product of two vectors from H as the inner product of corresponding functions in L2. So this is the integral of x, h of x, k of x, d gamma of x. So then the Cameron-Martin space becomes a Hilbert space. Actually, it is isomorphic to the space x star, to the closure in L2 of centered linear functions. Now we will study the question about shifts of Gaussian measures. So let G belong to the space x star gamma. We know that G is a centered Gaussian random variable with the density, with the variance I denoted sigma G. Then if we consider a new measure, which is absolutely continuous with respect to gamma and has the following density, then we get a Gaussian measure. It has the same covariance operator as gamma, and mean is shifted by Rg. To check this, consider first some linear continuous functional and the function phi of a real argument z, which is defined as follows. Now, L of x minus a minus that g of x belongs to this closure. So it has a Gaussian distribution with mean 0, and the variance, it will be the variance of L, which is LRL, minus 2 integrals of the product Z, L, and G, which is L of RG, and plus the variance of ZG, which is Z square sigma G squared. Okay, so we computed function phi. It is easy to check that it can be actually defined for all complex values of Z. And it is an analytic function of Z. This follows from integrability properties of the Gaussian measure. If we take the value of this function when Z is equal to I, so what we will get, this will cancel. We will get E, I, L, RG plus A minus 1/2 LRL. And on the other hand, this function is the integral. This function is the integral of exponent I L x I L x. This A cancels. Times exponent. So now that is equal to I, so we get g of x minus 1/2 sigma g squared d gamma. And this is a Gaussian measure, and we computed the mean and covariance operator. From this result, it follows that the shift of a Gaussian measure by the vector of Cameron-Martin space makes it equivalent measure, and we know the density of the shifted measure with respect to not shifted. The density is the exponent of function g that corresponds to h minus 1/2 squared norm of h. Okay, and next consider the case when h is not in the Cameron-Martin space. Then it turns out that the shifted measure will be singular to initial measure gamma. The fact that h is not in the Cameron-Martin space means that the Cameron-Martin norm is infinite. So we can find functionals that have a variance 1 and such that they take as large values as we need on the vector h. Now estimate the total variation distance between shifted measure gamma and non-shifted measure gamma. When we consider images of measures, the total variation distance decreases. And since L is linear functional, the image of shifted measure by L is the same as the shift of the image measured by L of H. And the total variation distance. Now, this shifted measure is a Gaussian measure on the real line. So it is absolutely continuous. And then the total variation distance will be equal to the integral of the absolute value of difference of densities, so which is 1 minus exponent T L of H minus 1/2 L of H squared. Using following inequality that for positive numbers A and B, absolute value of A minus B is bigger than root of A minus root of B squared. We can estimate it further as follows. So it will be integral of the square, and here 1 minus the root of exponent. And now let's compute it. It will be the integral of 1 minus 2 exponent 1/2 T L H minus 1/4 L H squared plus exponent squared. And half L of H squared. And we integrate with respect to the standard Gaussian measure. But this is just the density, so the integral will give 1. And here, the integral of this exponent will give exponent minus 1/4 L of H squared times exponent 1/2 and the square of coefficient near t. So L of H squared over 4. Which will give exponent minus 1/8 L of H squared. Okay, and since L of H can be taken as large as possible, we will get in the limit 2. So in fact, the total variation distance between shifted measure and not shifted measure is equal to 2. Okay, but these are probability measures, so they must be singular. Okay, so next time we will continue studying the properties of Gaussian measures, and we will consider also some properties of the Cameron-Martin space and 0-1 laws. Thank you for the attention. Maybe you have questions.